Hello, this is Lab 3, Magnetic Field of a Bar Magnet for Physics 2212. A brief introduction to this lab. The purpose of this lab was to compare experimental to theoretical values of magnetic field through an experiment using a magnetometer on a phone in which we determined, we're using the data as seen on the right, kind of a sneak peek into the results. The degree at which the magnetic field drops off in respect to distance, along with visualizing said magnetic field from the experimental data in GlowScript, and how the theoretical value differs very drastically due to many reasons that we'll mention later. On to some physics principles, interactions between magnetic fields, experimentally measuring the field with Earth's in mind. So one thing we had to do in the experiment was to be aware of Earth's magnetic field, as that affects the number. So we have to figure out which component we can isolate it to and then negate it by measuring it without the presence of the magnet. Equations, magnetic field due to dipole. Easiest ones, the perpendicular case and the parallel case, as seen here. Along with over here, we have a little sneak peek, sort of like free body diagram type thing into our results. White is the magnetic dipole in the middle. Green is our on-axis magnetic field. Blue is the off-axis, and the perpendicular, and purple is the off-axis. The system being the magnetic dipole, and the surroundings being the Earth and, well, everything else. On the code. So quick brief talk before that is right here is the equation used to find the magnitude of mu. So down here, this is the first function. This is the, it takes in the vector mu and the vector r, and using the equation shown in the Canvas assignment, we determine the direction and magnitude of the magnetic field. And this is covered up a little bit because it's all repetitive, but this is the code that written to display all of the arrows, where the axis, the direction of the r vector is defined earlier, and the direction of the b vector is going to be based on this equation right here. Onto the off-axis code. It's very similar code, very similar snippet to the last bit, just with a different observation location. Onto the results. So as you can see, as shown before, we've still kind of got those coils going that we want to see, where it comes out of one end of the magnet and goes into the other, goes out of the north end, goes into the south end. So some assumptions we made in this model, though, is that Earth is the only external field apart from the system. Now, when measuring the case, there could be wires in the tables, all that stuff that can cause induced magnetic fields to affect our results. However, we did our best to mitigate those by doing all of our work on the ground. Also, that the field is constant and propagates evenly through air. So, there's a whole bunch of stuff in air that just kind of gets in the way, and we just assume that none of that's real. And also, note, as asked in the assignment on Canvas, as the magnetometer moves closer to the magnet, the measured x component increased. That is because the closer we got to the magnet, the greater the strength the magnetometer read for the field. Here are our values down here. And yeah, the reason that the off-axis value is similar to those perpendicular values that you can see is because the off-axis value is just over a 1/4 inch away, and these are a 1/4 inch away. All right, discussion. First discussion question. If we hadn't oriented our experiment to compensate for north, I talked a little bit about this, but if a majority of the Earth's magnetic field wasn't in the y component, then it would be spread out between the other components and would not be canceled out, affecting the accuracy of this prediction, basically affecting the accuracy of our measured mu. And the second question, what if you were to stick two identical magnets together end to end and run each one again? I expect that there would be similar directions for the field, but greater magnitudes. The magnitude of the magnetic moment would be larger, partially because the magnet itself is bigger, but also there being more aligned internal components of the magnet to induce a larger field. Thank you.